Welcome to more of 106X on backtracking. So I decided to put this video together because we didn't quite cover everything I wanted to cover in class on Wednesday. So you can take a look at this video. The slides are the last part of the slides from the Wednesday lecture. They're all going to come up on the screen here. Anyway, so let's start back with maze solving. I went through some of this on Wednesday, but I'm just going to briefly go back through the basic idea here because we're going to have to solve this little maze here using a systematic method so that the computer can go in, it can solve the maze by checking basically all the solutions. And so what we do is, remember, we go in all four directions. We can only go north, east, south, and west here. And we're always going to go north, then east, then south, then west. And if we get to a point where we can't do either, we will end our recursive case, and that will basically backtrack through until we get to a point where we can check another position. Okay, so briefly, this is exactly what I went through the other day in class. We start at the top. We're going to be marking positions with a period and mark backtracking with a B. All right, so what do? We start at position 1, 1, and we mark it with a period, because if we see a period, we're going to have to not go back to that, not check that position if we get to a place in the maze where where there is a period there. So you'll see how that works when we get to the actual code. But the basic idea is, okay, try north first. All right, and if we try north from our position, we hit a wall, right? So then we try east, and we always try north, east, south, west. All right, so we can go east, so we mark where we are with a period, and then we end up in that location, and we start back over, because remember, we have to systematically check everything. So we check north, we can't go north, we can go east, so we mark it with a period, and we go to that location. Now we, again, try north first. So remember, this is systematic, and the computer is just dumb. It can't see an overview of the entire maze. So it just has to know its own local position, and it says, look, can I go north? Nope. In this case, can I go east also fails. So can I go south? Yes, you can go south. Right here, we can keep going south. And we go south, mark it. All right, we get to here. What do? Well, we try north, okay? We basically say, look, we try north, but there's a period there. So we don't go there if there's a period where we just came from. Okay, so then we try east, can't go east. We then try south, we can go south. Now, this continues. We get to this point, we try north, there's a period there. We try east, we can't go east, there's a wall there, we go south. And this just continues. And we end up following the path around here. Now we get to this position. Now, a human would say, great, I see the finish, I can just go south. But we can't do that as the computer because there's no method for heuristically determining which direction we go. We have said that we always go north first. Okay, now there might be some other heuristic. In fact, later in the class we'll end up talking about shortest paths and a type of path finding called A star, which can, as it turns out, heuristically choose a proper direction, so it actually would be able to go south. But in our case, so far, all we're doing is we're saying we will go north. All right, well, we can go north, and we can continue to go north until, and then we continue, and then we end up going west and then south, just like we did before, and we end up in this spot here. Now, if we try to go north, right, if we try to go north, well, there's a period there, so we're not going to do that. If we try to go east, there's a wall, we can't do that. If we try to go south, there's a wall. If we try to go west, there's a wall. Now, in this case, we have exhausted all four of our possible choices, right? There's no other way we can go. And so in our recursive solution, which we'll see the code for in a few minutes, you now say, oh, okay, I'm going to return from this function. I've tried all my different directions, and I'm going to return from the function. And as you return from that function, you mark where you've been with a B, just so we can see it on the map. And it will actually backtrack like this. When we backtrack there, we backtrack there, and we continue backtracking by just returning from the function and marking where we've been as a B until we get all the way back to where we started. Now, let's think about what happened when we were here before. We went north, right? And now we're going to go east again. Okay, we tried east, and that's a wall, so we try south. We can go south, and then we try north again, but there's a period there. We try east again, and there's a wall, and we finally go south, and there's the finish. Okay, so this is going to be systematic, but it will involve some backtracking. But we will find the end of the maze. Okay, so the total number of steps here, and in fact, I will put this at the end of the presentation here. Total number of steps is 71 steps to go. Basically, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 paces, basically, took 71 steps in the actual program. It seems like a lot of steps. The good news is computers are pretty darn fast. So you can see how it will actually solve the maze, but it's doing it in a way that's systematic, which doesn't necessarily lead to a particularly fast solution. Okay, so that's maze solving. Let's actually see some of the code. First of all, let's think about the base cases for this. All right, remember, we have to have a case for all valid inputs, we have to have base cases, and we have to move forward or make forward progress towards the base case. Sometimes we're actually backtracking, which is the return from these, and that's not forward progress, but that's just getting back to where we can make forward progress again. So let's think about the base cases. Well, if we go out of bounds on the grid, like in other words, if we would actually leave below 0, 0, or to the left of 0, or to the right of 8 in this case, that would be out of bounds. That's a base case. But in our map, as it turns out, or our mazes, as it turns out, I've put walls around everything. So that'll actually never happen. You'll never have to worry about that, but we should think about it anyway. Okay. Another case is if we hit a backtracked position, right? We actually won't happen. That won't happen either because of the way the once we actually mark a position as backtracked, you'll never get there again, as it turns out. If we hit a wall, then definitely that's where we have to say, oh, can't go that direction, and we return. And if we hit a position we've seen before, same thing. So that's why we kind of mark all these things, so that we know where we've been and we can continue making forward progress. Okay, and of course, if we find the finish, we also get a base case, meaning we're complete and we're done. All right. If we return true, this is the way we're going to build this. If we return true, we've solved the maze. If we return false, we have not solved the maze. The only thing that's allowed to return true, basically, is if there is an F for finish. Okay? So the cases that don't actually matter, like going out of bounds or going to actually hitting a B backtracked, are not going to be base cases we're going to worry about. So these are really the three base cases we have. If we hit a wall, we return false. If we hit a period, we return false because we've been there. And if we hit the finish, then we return true because we've finished the maze. All right. At the end of the, like after we check the base cases, well, we immediately mark where we've been, because then we're about to go check the actual path, and you don't want to. If you go down that path, you don't want to. You want the period to be there so that that follow-on path can make a check in the direction it just came from and see a period, so it doesn't try to go that way. All right, so we mark the maze position as a period with a period. All right, now here's the go check in all directions here. Okay, this is the idea where we're going to do the recursion. Okay, to go north, let's look at what we have to do. Well, we have to solve the maze by trying one previous row, because one less row is on our maze north. And so we just say we're going to call the position, and the new position is going to be the row -1 in the same column we're in, and we pass the maze along. Okay, and by the way, the maze in this case is keeping track of all of the other data that we need, for instance, all the periods and where the walls are and all that. So that's why we pass this along. Notice we are passing it by reference, so it's not like we're making copies and copies of this maze. We're just passing the reference to it. So if that's the way we go north, well, to go east, we have to change the column, and in this case, column +1. So basically, to go east, it's going to be exactly the same idea here, and we can do that. Now, by the way, I'm looking at this now, and we definitely don't need the equals true. You could have just said if solve maze recursive print return true. In other words, it's going to be true. But I suppose that makes it a little less or a little easier to understand seeing it this way, but it's not completely necessary. Okay, so if you look at all of them, east is going to be row col +1, south is going to be row +1 col, and west is going to be row col -1. Okay? And if we get through all of those and none of them have returned true, by the way, if we do return true, well, that was part of the path, right? Now, if we don't return true, well, that means we've hit a position where we didn't get to the finish and we can't go in any other directions because we tried them all. We tried north, we tried east, we tried south, we tried west. So now we will hit, now we will say, look, fine, mark it with a B for, I'm about to backtrack here, and return false, meaning we didn't find a path down this direction. Okay. All right. So now let's actually look at some of the code in general, and then we'll actually run it. So this is the same idea. This is all the same thing here. Yeah, I did change this here, so we don't need the actual equals true. And this is the thing. Now this code has lots of extra stuff in it to build. It actually has to build a maze, and then I've got extra code if you wanted to print out all the details, so you can do that. And let's take a look at a run here. So let's run this, and we will see that we can, here, I'll bump up the font a little bit. Make the font say bigger. Okay, and we can say, okay, let's solve a maze of size 5. All right, and there we go, and here's the original maze. And again, it doesn't look so great with the X's here, but the blank spots are the path here. Okay, so to solve this maze, I'm doing the mouse here. It's just like this, right? And in this case, the maze is perfect. There's no backtracking necessary. All right, let's try this again. I'm probably gonna have to change the font size again. I won't change the font size because I'll make it a bigger one. Let's solve a maze of size 10. Okay, here's the maze of size 10. I will zoom in a little bit here. And we can see that here's the maze of size 10, and it's a little more involved to get there. Our maze goes down here, goes down a bunch of paths here, it looks like. Gets down, gets up here, goes up here, goes up here, goes up here, goes up here, down here, down here. Unfortunately, here it should have gone south, as it turns out, but guess what? It went north because that's where we did it, and lots of backtracking. It looked at the entire rest of the maze up here and had to backtrack through all of that. But anyway, it eventually gets back down here and then goes in the correct direction to solve the maze. Okay, so that's how this little program works. Feel free to run this on your own and check out the code, but the meat of it is this recursive idea of check all the different possible solutions and just return up through the decision tree as you get to other solutions, or as you find that you didn't solve the maze. Okay, all right, so let's get back to the next problem that I wanted to cover. So this is actually a famous problem called the Knapsack Problem. This is another find the best solution to the problem. It's not a find any solution or tell how many solutions it is. It's one of these find the best solution, which means we have to exhaustively search all the solutions. And it's an interesting problem. Here's how it goes. Given a knapsack or a backpack, you know the backpack can hold some amount of weight. And you have a whole bunch of things that you might carry in that backpack, and they each have their own value, okay? So like for instance, this one has a weight of 12 kilograms and a value of 4. This one has a weight of 2 kilograms and a value of 2. So this is worth more per kilogram. So as it turns out, if you had, and in fact this one is $2 as well, but only 1 kilogram. So what we're trying to do is maximize the number of things that we can, maximize the value that we can get out of putting the things available into our knapsack. In other words, we can only fit so many of our items into the knapsack because of the weight restriction, but we want to find the value, the best value, given the items that we have. So this is an exhaustive search, and the way we're going to do it is going to involve backtracking. Okay? All right, so determine a subset of objects so that the sum of their weights is less than or equal to the target weight, and the sum of their values is maximized. So the sum of the values is maximized, the part we're worried about. The main part, the other part is, oh, we can't put too many things in our knapsack so that the weight is over. Okay? All right. Here's what we're going to do. I briefly mentioned in class these structs. This will become nice. We could pass a couple vectors of different items through, but let's pass a struct, a vector of objects where the object has both a weight and a value. Okay, we're going to assume that they are both equal or greater than 0. In other words, you can't have a negative weight, which makes sense, but you also can't have a negative value. If we put negative values, we might have to change some of this. In fact, I don't think for the solution we have, we would have to change the solution for negative values. For negative weights, we would. Well, we might not as well, but anyway, regardless, we're going to kind of make this real-life things. Okay, so let's write the actual function. Here's the function we're going to write. It's called fill knapsack. We're going to give it a vector of these objects, and we're going to give it some target weight. In other words, that's how much the backpack can hold. All right, and we're going to consider all possible combinations, and we're going to return the maximum possible sum of values. In other words, some best score, if you will. Okay, so let's see what the basic idea here is. By the way, you should probably pause the video if you want to think about this yourself. And by the way, this is a very good problem for a midterm or a final. In fact, I believe it was a final exam problem a couple of quarters ago. So here's the solution that I thought of, or that I guess the solution that was on the final, because I looked at the final exam key. So we want to keep track of the weight, obviously, and keep track of the best score. Okay, so as we go through this recursive solution, we're going to say, look, make sure we know what the weight remaining is, basically, and keep track of the amount of things we can still, or how much weight we can still put in the backpack, and keep track of how much score we have so far. We're going to have to loop over all the items. Okay, there are ways of doing this with subsets, but this is the way a potential solution is: loop over all the items, add the value of the particular item to the knapsack, subtract the weight because we just added it to the knapsack. In other words, we can't, if we put a 12 kilogram object into a 15 kilogram bag, we can only have 3 kilograms of weight left to put in the bag. And then remove that object from our list of objects. It's not actually written here, but we want to do that once we check that object. If we put too many items into the bag, in other words, if the total weight goes above the original that we had, in other words, if the weight we're removing from goes below 0, then we have to return the solution of 0 because we're overweight. Okay, and in this case, we have to have a helper function. There's really no way to you might be able to get away with this without a helper function. In fact, you probably could get away with this without a helper function, but it's actually much easier to do it with a helper function. In this case, we're going to pass along a reference to the objects. We're going to pass along the weight that is still allowed to be put in the backpack, and whatever our best score so far is, because that's how we're going to make a decision about whether or not we've found the best score. Okay? All right, let's see what we have here. This is just the basic original what we're given. We have the object struct and the original function, and the original function is just going to call the recursive function with a base value of, gives the objects, gives the target weight, and we say that we don't have any best score yet. Well, best score is still 0 because there's nothing in our knapsack. Okay, all right, let's take a look at the solution and we'll go over this piece by piece. So here's the idea. An initial base case, well, let's look at it in general. Basically, we're doing a base case, we are keeping track of some scores from the object that we're checking, and then we are looping through all the objects and making a recursive call. We are removing an object each time through the loop, and we have to replace that object back into the number of objects so that the recursive call, the next iteration through the loop can use the objects in their original form. In other words, we're trying one at a time, and we need to ensure that all of our solutions get the same number minus the one we've removed. So you can't just remove them all and never replace them. Besides the fact that because we're doing all this with references, we need to insert the object back in so that our original object remains the same. You don't want to return an object to a calling function that's been modified unless they say it can. Okay, so that's the base thing. Let's go through this in a little more detail. Here's our little base case of if the weight is less than 0, we're going to return 0. In other words, if in the recursion we remove an object, we add that object to the backpack, and then we check it, and we call the recursive function, and the recursive function, the weight is less than 0, well, it means we added too many things to our backpack. Now, we could have done this with a bit of arm's length recursion in the sense that we could have, before adding the object or calling the recursive function, we could have said, look, if the current weight is less than 0, skip this one. But that's arm's length, and we might as well let the base case be, if we've added too many items, then then return 0. It's a little bit simpler, and it removes the idea that we have to kind of look ahead. We're not looking ahead at all. We're saying, what happens now? Oh, I got a backpack with too many things in it. Okay, all right. We're going to keep track of the best score locally. Now, this part is maybe a little different than some other problems. If you keep track of the best score locally, that's because we're going to go through this loop and see what the best score is from all of those solutions. So you need to keep the best score in a local sense, because the best score overall is what we will get from, what we will return from our little check of all the objects that we have access to so far. Okay, now we're going to basically loop through all the objects, and we're going to first get the object out of the ith object in our loop out of the number of objects, and we're going to update our values. So we're going to have a current value, which is basically our best score so far, plus the original object's value, in other words, the object we just pulled out, and then we're going to update the weight by saying, oh, we just added it to the backpack, so we need to subtract the amount of weight we have left. Okay, and then this is now the situation that we're going to recurse on. So we remove the object, and then we call our recursive function. Now let's think about what we've done here. We've said, okay, we've got one fewer object in it. It's the fewer object at position I that we just removed. So if we started with 4 objects, the first time through the loop, we're going to have the last 3 objects because we removed the first one. Second time through, we're going to have objects 1, 3, and 4. And, or I should say 0, 2, and 3, if we base 0-based counting here. And then we're going to pass along the weight that we just got from, or that we just subtracted out. In other words, the backpack weight is going to be less. We can hold less than what we started with because of the fact that we've added we've added an object to the backpack, and then we've added some value, meaning that whatever the best value was before, we're going to add to it. So that's the recursive call, and we have to store the value that we get back from that, because that's what that recursive call says is its best value. Now this part's a little interesting. Once we get a value back, we have to say, look, is this the best of all the solutions we've looked through? So if we've got 4 items in the backpack, we're going to go through 4 different solutions here, and we're going to get 4 values back. Well, one of those 4 is going to be either the best value or less than the best value. In other words, let's say everything remaining overloads the backpack, it would be 0. But what we do is we're just doing a little check, and we're saying if we want this value that's returned to us is better than our local best score, update the local best score. We can do better than what we currently knew we could do. All right, this part's important. Replace the object back in for the follow-on loop. And then finally, we say, okay, after all of this looping, we're going to have some local best score, which we're going to return to the calling function. Now, interestingly, the first time this recursive function gets called, what it will return is the actual best score, because locally to it, it is kind of like the root of the tree, and in fact it is the root of the decision tree, and its local best score will be the actual best score. But each one of the recursive functions that's called will also have its own best score, and we are keeping track of the overall best score, which we finally return to the original calling function. Okay, so that's the whole function there. Let's actually look at the code itself. Have this up here, and we'll actually see it run. I have a couple different solutions, a couple different values and weights that we can check here for this set of values and weights, where the value is 12, the weight's 4, 10, 6, 8, 5, etc., and I have a target weight of 18, it should produce a result of 44. This code is exactly what we saw before. It's really not that long. This is the same code that we saw in the slides, and might as well run it and see what we get. Okay, so there we go. The best solution has a best score of 44. If you can't see that, there we go. And so I suppose that's not the most interesting example. If we wanted to keep track of the objects that we put in there, we would need to do that by passing along some other, probably a vector of items that we put into the bag, and you'd have to keep track of that as well. All right, so that's all the other things I wanted to talk about with recursive backtracking. And if you have any questions, feel free to ask them in class, put them on Piazza, or send me an email. All right, thanks a lot.